All right, today is the second review session, right? And we have a midterm exam next week. And I have prepared some problems, but I'll go through them unless you have questions. But I was hoping that you were doing some problems on the weekend that you have questions. So, any questions? Example problems? Yeah, excellent. Let's go over this. Here's the 3.8-2. It says find the zero state response by zero state of n for the linear time invariant discrete time system that has an input x of n given as 3 to the n minus 1 u of n plus 2 and h of n is equal to 1/2 delta of n minus 2 minus 2 to the n plus 1 n minus 3. So this is all now notation of nightmare. So let's just first see what is happening here. So in principle, this is not a hard problem, right? You have a system, you have input, and you have impulse response. So your zero state output of n is going to be x of n convolved with h of n. Right? But there's some, and I hope this is not a typo. So let's just unwrap this one and see what it looks like. H of n is equal to 1/2 delta of n minus 2 times u of n minus 3 minus 2 n plus 1 times u of n minus 3. Just as it's written here, right? Because we can talk about this with this and then this with this here. Now let's take a look at this one. What is this? First of all, I'm missing something. What am I missing? Minus 1/2 here, right? Let's take a look at this one here. This is a delta. Let's just, so this is 0, 1, 2, 3. Right? Where is this delta? It's here. Right? Where is this u function starting?
1/2.
So it's starting from here. Actually, I should just, and then continuing this way. So what is the product of these two?
0.
0, right? So this whole thing is 0. So essentially, your h of n, your impulse response here, is minus 2 to the n, actually just minus 2 minus 2 to the n, u of n minus 3. So that's your impulse response. Okay? So once you have it this way, then it becomes relatively easy. Now let's see what happens. So y zero state of n becomes x of, I guess I can write it out, m goes from minus infinity to plus infinity, x of m times h of n minus m. In our case, this becomes summation. X of m, x is given here, so it's going to be 3 to the n minus 1 u of n plus 2, right? That's your x of m. And h is going to be this here, but I would have to, instead of n, I would have to put n minus n. So this becomes times minus 2 to n minus m times u of n minus m minus 3. Okay? And now I have to look at integration. M summation, where does it start? This u here tells me there is no need to integrate before minus 2, right? So I should integrate m equals to minus 2, because for m smaller than minus 2, the argument of this becomes negative, and the u function makes everything 0.
Excuse me, can we assume k equal to m plus 2? I think it would be easier.
Okay, let's discuss that. Let me just substitute. Maybe we don't evaluate this whole thing, but your idea is very good, and let me just discuss it in a second. So this is m goes from minus 2. Here, you can see that as soon as n becomes larger than n minus 3, this becomes equal to 0. So this goes from minus 2 to n minus 3, right? And then I can get rid of these 2. So I guess this is sum. M goes from minus 2 to n minus 3, 3 to the n minus 1. I can put minus outside, 2 to the n minus n. And then I need to sum this, right? So that's one way. You wanna, let's just carry this couple more steps. So 2 to the n goes outside. I can say minus sum m goes from minus 2 to n minus 3. 3 to the n, 3 to the m over 2 to the n times 1 over 3. And this is, let's see, I can say minus 2 to the n over 3, sum n goes from minus 2 to n minus 3, 3 halves over n. Okay, so that's one way of dealing with this. The other way is to look at and use our knowledge on what happens when you shift stuff around, right? Go ahead.
Yeah, actually, it's not supposed to be closed.
Where?
Yeah, that.
Here?
No.
Why would it be plus?
You have minus half.
Minus, huh?
The minus sign to convert half into minus 2 is supposed to be.
But you cannot bring this minus 1 over here, right? Because it's inside this n plus 1, right? The way how you should see this, let me put it here. This becomes minus 1 half times minus 1 to the n plus 1 times 2 to the n plus 1. You see that? Right? So then, this 2 and this plus 1 cancels. And I guess you can say then this minus 1, so this becomes minus 1 to the n times 2 to the n, which you can say is minus 1 minus 2 to the n. And then you can have plus, which is the same as what I have here. Right, so I guess you're right.
So you still currently negative through, right? That's what you're trying to say.
Say again?
You're supposed to have a positive instead of negative into minus 2.
It will work out somehow. I mean, this minus would take one minus from here. I mean, it's just a matter of, I didn't want to complicate it. Both of these are accurate, this one and this one, they're equivalent completely. Right? It's just that in this case, I left the minus outside, but in this case, I took one minus and stick it up front. So, oh, I see what you're saying. It should be an n plus 1 here.
Yeah.
Yeah, this is what you're saying.
But then that would change your 1/2 that you pulled in to cancel it.
Ah, okay.
Yeah, no,
So, yeah.
Yeah.
Okay.
yeah.
So that,
Yeah.
then all the way up there it would change.
Yeah, so it will change here, yeah, as well, right? And this will go away. Right. Right. But, so that's the way how you do it, I guess, direct. The second way to treat this is this. Let's say x of n is given to me as 3 to the n minus 1. U of, and this is very good that you asked this question, because this is the way to do it. H of n is going to be equal to, I have it there, minus 2 to the n, u of n minus 3. Okay? So, let me define x1 of n, which, or let me call this k, which is essentially this one, but instead of n, I'm going to substitute n, in this case, introduce substitution. K equal to n plus 2. So from here, n is equal to k minus 2, right? And then I can say here, or let me think a little bit before I go.
So how if we just start function from minus 2 to n, minus 2 to infinity basically, because u of n plus 2 is just a shifted version to, so the signal will start basically from minus 2.
Which one will start?
X of n.
Yes, I know.
So,
I know.
so why
But
we
here's
substitute-
what I was gonna suggest is this. Here's what we know. There's x of n, right? I can define a new signal that starts at 0, right? And then because I know that this one starts at minus 2, take the output and just bring it 2 samples up, right? So if I define a signal x1 of n, which is equal to, now its tricky part is I need to make sure that these numbers correspond. So when n is equal to minus 2, this is 1 over 3 to minus 3, right?
Mm-hmm.
So it's going to be, let me just draw it so it will be easier to think about it. So this is minus 1, minus 2. So at minus 2, this is 3 to the minus 3. Then at minus 1, this is 3 to the minus 2. At 0, this is 3 to the minus 1. And then it goes 3 to the 0, and then so on, right? So if I define a signal, x1 of n, that it says something like this, 3 to the n minus 3 u of n, that signal starts at 0, and it looks exactly like this, right? It just starts at 0. It moves 0 point, okay? So that's the first signal. Did you follow what I did? So that's x1 of n. So now if I feed this x1 of n into this system here, I'm going to get y1 of n. But what do I know about y1 of n? Since x1 of n is advanced, or I should say delayed version of this x of n by 2 samples, y1 of n is going to be delayed version of y of n, right? So all I need to say here is if I get y1 of n is y of n is going to be y1 of n plus 2. So once I get y1 of n, I just advance that by 2 samples and I get my y of n.
So can we also delay the h of n as well?
That's the next step, right? So get everything, you know, aligned with 0, calculate the output, and then shift left and right as you need to. So I know that if I have so that's the just doing x of n. Now if I look at h of n, I can define so this is x of n. Let me do h of n. How does h of n look like?
Divided by
H
3.
of n starts at 2, right? And this is 1, 2. And at 2, its value, it's
Starts at 3.
no, it starts at it starts at 3. Sorry, 3. So and when n is equal to 3, this is minus 2 to the 3, right? So this is minus 2 to the 3. And then the next one is minus 2 to the 4, and so on, right? So I can define h1 of n, let me put it here, h1 of n to be minus 2 n plus 3 times u of n. Okay? That's an impulse response of the system that it's the same as h of n. It is just advanced in time by 3. So if I determine the output of this system to the input, then the output of the original system I would get by delaying that by 3, right? So if I do this, if I have a, let's say here, x of n, and I put that through h1 of n, and I get some y2 of n, then really y of n is going to be y2 of n minus 3. And then I look at this, okay, now what happens if instead of x I put x1, and instead of h I put h1? Then I'm going to get an output that I first need to advance by 2 and then delayed by 1. And then really what I'm going to say now is y let's say x, y star of n, I'm going to calculate as x1 of n convolved with h1 of n. And then I'm going to get proper y of n by taking whatever is y star of n and then delay it by 1. Okay? Did you follow the whole process? And that's the way to do it, because otherwise it can get crazy with these things. Right? So now that we have these things, then let's just formulate this. It becomes relatively easy. So x1 of n convolved with h1 of n becomes sum when n goes from minus infinity to plus infinity. x1 of n is this guy. So it's 3 to the n minus 3, m, u of m. times, and then h1 of n is times minus 2 to the n minus m plus 3 times u of n minus m. What did I do? This is my x of m, and this is x1 of m, and this is h1 of n minus m. Right? And then you just expand this a little bit, so this becomes sum when n goes from 0 to n. Why? Because for 0, this guy kills everything below 0, and this guy kills everything above n. And then you have just 3 to the m minus 3 divided times actually minus 2 to the n times minus 2 to minus m plus 3. And minus 2 to the n goes on the side. And then I have sum, m goes from 0 to n. So it's 3 to the divided by minus 2, everything to n minus 3. Okay. And this one is easy to sum. What I'm going to do is take 3 over minus 2 to the minus 3 outside. So this becomes minus 2 to the n. 3 over minus 2 to minus 3. And then sum n goes from 0 to n. 3 over minus 2 to the n. Right? And here, this becomes minus 2 to the n. I can say this is minus 2/3 to the power of 3. And this is 1 minus minus 3 over 2 to the n plus 1 over 1 minus minus 3. Right? And then you just clean this up a little bit. And then once I get this one, then the true answer is going to be wherever I see n, I will put n minus 1. And that would be.
Further away, can we say, assume k here, before we determine the limit of formation, we assume k equal to m plus 2.
Which relation, which equation are you talking about?
The second line.
Here?
Yeah. K equals to m plus 2. Yeah.
And then k goes from 0
to
yeah.
n minus 1.
Yeah. Yeah. You can do that too. But really, this is how I want you to approach these problems. Make everything, shift to 0, and then the overall response is whatever many shifts in the input and output you need to do to, in this case, we needed to shift the X signal 3 units to the right, and we needed to shift H signal. How is it this? Where is it? We need to shift H to, we needed to shift X 2 units to the right, and we needed to shift H 3 units to the left. So at the end, we calculate the results of these to align with 0, and then because it's 2 units to the left and 3 units to the right that you need to shift, and ultimately you need to shift everything 1 unit to the right. That's a good problem. Any other? Come on, Candelaria.
Wait. I have a problem. 364. Boring?
This is the shift section.
Yeah.
365?
365, sorry.
That's what we meant, 365.
365.
365, okay.
Yeah.
Group effort over there?
Is it in this book 365?
Yes, sir.
Yes, 365. Leonardo Kostanic.
Okay, oh,
Just tell us from the Twitter.
Fibonacci numbers, right?
Yes, Fibonacci.
Yeah, Fibonacci.
Okay.
I'm wrong, I'm sorry.
All right, so Fibonacci numbers are defined, let me just list them here, 0, 1. So you start with 0 and 1, and let me call f of 0 is equal to 0, f of 1 is equal to 1, and then f of n plus 2 is equal to f of n plus 1 plus f of n, right? For n equal to 0, 1, 2, and so on. That's how we define Fibonacci numbers. Each one is the sum of the previous two ones, right? So if you look at 0, 1, the next one is going to be 1, then the following is 2, then 3, and so on. Okay, so find the constant coefficient difference equation whose zero input response with auxiliary conditions is sequence. So I already kind of wrote it here, right? If you look at the difference equation where f n plus 2 minus f of n plus 1 minus f of n is equal to 0. That's a difference equation in our form. It's a zero input, so there's nothing on the right-hand side, and the outputs are these f's, right? So that's the difference equation, and then it says find the characteristic roots and then essentially solve this for any arbitrary number. So if you look at the, so let's find f0 input of n. This would be the nth Fibonacci number, right? How do we find it? Well, we have our process where we first find the characteristic equation, find the roots, find the general form of the zero input response, and then use these two initial conditions to find the coefficients that will make them satisfy. So in our case here, the characteristic equation, Q of gamma, is going to be gamma squared minus gamma minus 1. That has to be equal to 0. So gamma 1, 2 is going to be 1 plus minus square root. B squared is 1 plus minus 4ac, which is plus 4 divided by 2. So you have gamma 1, 2 as 1/2 plus minus square root of 5 over 2. In other words, gamma 1 is 1 plus square root of 5 over 2, and gamma 2 is 1 minus square root of 5 over 2. Right? So these are our two characteristic roots. We know that our zero input response, which is the nth Fibonacci number, has to be in the form C1 times gamma 1 to the n plus C2 gamma 2 to the n. In our case, this is C1, 1 plus square root of 5 over 2 to the power of n, plus C2, 1 minus square root of 5 over 2 to the n power. That's the general form that Fibonacci numbers need to have. But we also have two initial conditions. When n is equal to 0, the f of 0, which is actually, sorry, let me correct this. This is for n equals 0, 1, 2, right? So this would be yeah. I can say f of 0 is going to be C1 plus C2, and that has to be equal to 0. F of 1 is going to be C1, 1 plus square root of 5 over 2, plus C2, 1 plus square root of 5 over 2, and that has to be equal to 1. And from here I can solve for the two of them, right? There's a minus here. For here, I learned that C1 is equal to minus C2. And if I plug that in here, I get, for example, C1, 1 plus square root of 5 divided by 2, minus C1, 1 minus square root of 5 divided by 2 has to be equal to 1. So if you look at here, square root of 5 and square root of 5 cancels. I have, no, it doesn't cancel. Those are the ones that add, right? So I have square root of 5 over 2 minus square root of 5 over 2. So I have 2 square root of 5s over 2. So C1 times square root of 5 has to be equal to 1. So C1 is 1 over square root of 5. And of course C2 is equal to minus 1 over square root of 5. And your general form for Fibonacci number is going to be 1 over square root of 5, 1 plus square root of 5 over 2 to the end, and minus 1 over square root of 5, 1 plus square root of 5 over 2. And then you can just plug n into this and get the value of whatever and
Whatever they ask.
yeah, whatever they ask. Okay? Now, the remarkable thing to me is, look at these n's. Fibonacci numbers have to be integers, right? Because they're always sum of the two integers, so they're always integers. But yet, they're composed of these irrational numbers. Square root of 5 is not a rational number, right? So somehow it magically works, so that when you do all of these n's, squaring and taking a square root and then taking to the power, everything right of the decimal point cancels. And you get an integer number.
Was it 2, 4? 4, 2, 4?
4, 2,
4, 2, 4, 4, 2, 4?
Yeah.
2, 4, 4.
2,
2,
4.
4.
2,
Chapter 2.
chapter 2.
There was some discussion as to what C actually looks like.
I'll see, yeah, the circuit.
What?
The circuit, right?
No.
Just tell me what problem.
2.4-24, page 239.
Okay.
Back in chapter 3.
Oh,
The 2, 4-24.
yeah.
I'm sorry, Professor. About the Fibonacci things, before we go to that. Do we need to put like some integers to prove that the cyanatic 0 and 1 is the first and second Fibonacci number?
That's given to you. That's given to you, right?
Okay.
Yeah. That's given to you. If you read the problem, it's given to you. The first two Fibonacci numbers are 0 and 1, and then that's how you start the sequence. Otherwise, you cannot determine it uniquely, because this is a difference equation of the second order, and you know that 0 input response to the second order difference equation has 2 coefficients. That gives you a family of curves that satisfy this difference equation. For any C1 and C2, this would work. But we need specific C1s and C2s for which these 2 points are anchored.
Yeah.
Yeah. So out of infinitely many possibilities, you just choose one. Right? That's why you need those starting points, and they give you those starting points in the problem. So this is a problem 2-4, 2.424. it says linear time invariant system has an impulse response in the form h1 of t is equal to 1 minus t u of t minus u of t minus 1. And okay, those are two systems. So this is H1. H2 of t is a different one that has an impulse response t, u of t plus 2 minus u of t minus 2. Carefully sketch the functions like H1 and H2. I assume that the two systems are connected in parallel. Carefully plot the equivalent impulse response. Assume that two systems are connected in cascade. And carefully plot the equivalent impulse response. Okay.
Hard sees the word.
Okay, because it's a convolution, right?
Yes.
Okay. So let's start. But let's start first by plotting this so that we know what we are dealing with. So H1 of t, you have two u functions which essentially form a box between 0 and 1, right? This cuts everything before 0. This cuts everything after 1, right? So we have this box. And within this box, this is how the H1 of t looks like. So this is it. It's this triangle that is between 0 and 1, and with the highest magnitude here of 1. H2 of t now you have, this is a pulse again, but goes from minus 2 to 2, right? And then the interval it is equal to t. So this is 1, 2, minus 1, minus 2. And this is this function. Right? So this is how the function looks like. So this is our H2 of t. Now, if I connect them, since I already kind of solved, this is part A. If the two systems are collected in parallel, how does the overall impulse response look like as the sum of the two? We saw that if you have two systems in parallel, the overall impulse response is the sum of the two impulse responses. So for parallel, this was part B. The equivalent impulse response, I'm just going to sketch it and not worry about the mathematical formulation. Before 0, I have this. Actually, minus 1, minus 2. So it goes to minus 2 here. And then here I have to add this to this. So essentially there's one guy here. So it goes as a square. And then it kind of ends up like this, right? It's a weird looking thing, but so this is equivalent one, right? This is 1, 2, 1, 2, minus 2. So that's how, if I didn't make any mistakes, this is how equivalent equivalent impulse response looks like for the part. Now for the guys connected in series or cascaded, then H equivalent of t is going to be H1 of t convolved with H2 of t. And now we have essentially these two guys. I'm going to use the same trick as I did before. I'm going to define H2 prime of t as t t minus 2 times u of t minus u of t minus 4. What is this? This is the same guy as this one, but it starts from 0. Right? So I'm going to look at the first p prime of t as h1 of t and 2 prime of t. And then I can determine the equivalent impulse response by advancing everything by 2 units. Right? Because I delayed, I took this one, delayed it, so everything is causal. I'm going to calculate the response of the causal system. And then because this one starts 2 units before, I'm going to advance everything by 2. So now that I have this listed, let's substitute. So this is integral when tau goes from minus infinity to plus infinity. H1 of tau, which is this guy, so it's going to be 1 minus tau. And let me write this. I can say u of tau minus u of tau minus 1 multiplied by this one, but t minus tau. So it's going to be t minus tau minus 2 times u of t minus tau minus u of t minus tau minus 4. And now it's the question of evaluating this. Do I need to evaluate this? Yeah. That's the tricky part, right? So let me think. It's really, you know.
Can we do it by just drawing? I mean,
You can.
H1 of t
Yeah,
and
you can.
moving it.
Yeah, you can, but let's see if we have a more elegant way. Another way how I would represent this is you can rewrite this. Let me rewrite this a little bit differently. I'm going to say this is tau goes from minus infinity to plus infinity. 1 minus tau times pulse at tau minus 1/2 over 1. Okay?
Hmm?
This is essentially pulse that it's centered at 1/2 and with a width of 1. Okay? And then the other guy is t minus tau minus 2 pulse of t minus tau minus 2 over 4. The tau. This is the pulse centered at t minus tau minus 2, and it has a length of 4.
Professor, when we attended it, we tried to break it up into like 3 or 4 intervals as
Yeah, we do a graphical method.
graphically as you.
You can, but then you have to be really careful, because then you actually have to walk. That's another way of doing it. To walk by t, and then see which integrals carry for a given t.
For a given range.
For given range, right? So it's really tedious. I'm just trying to see if there is a way of breaking this. And then really the good thing to do is scope it up and say, okay, this is duration of 1, this is duration of 4. So what's the duration of the whole signal in here? 5, right? So then you know that whatever you get needs to last for 5 units. And then you're right, you can flip and shift. That's one way.
That's what we want to see, though, because that's what we were arguing.
We were
when we got
hoping you'd be
together.
able to give us a true measure of what the real signal looked like.
Without flipping and
There-
shifting.
There's money on this, Professor, so.
Okay.
Not really.
Well, you kind of have a lot of trust in me all the while, right? So let's first see if we can do what you guys did. So follow your approach.
But our our B is off graphically because we are only have a width of 4, so we should have a width of 5, right?
Yes.
We're
This
going
is
from-
4, right?
But that convolved with that should be a width of 5,
Width of
right?
5, right?
It's only a width of 4.
What is width of 4?
No,
Negative
B
2 to 2.
B
This
is.
is H1, this is H2.
This is summation.
Oh, it's a summation.
So
Yeah.
summation, this is parallel. Now,
That's the
parallel
parallel.
is easy, right? The one that we struggle is the one where it's convolution. So what we need to do is evaluate this.
Yeah.
So let me rewrite it here and see if we can tackle it.
This.
So again, H 1 of n, and I'm going to do H 2 prime of n is equal to integral tau goes from minus infinity to plus infinity, and then I have 1 minus tau u of tau minus 1, 1 minus tau u of tau minus u of tau minus 1. And the other one is t minus 2 minus tau, right? T minus tau minus 2.
It would be easier to do the other way, I think.
It doesn't matter, right? Let's,
If it's not on the test, you won't have to go through it forever.
say again?
If it's not on the test, you don't have
No,
to.
but
do it.
let's at least.
Yeah,
It might be on the test now. Getting to like
problem is
it.
gonna be in the test.
Huh?
If it has a lot of
If the
problems,
exam is gonna come one problem,
There's
one is
one
gonna
problem.
be
Yeah.
we need math lab.
time.
So u of t minus tau minus u of t minus tau minus 4. This is the idea that you guys, I think that's one way of doing it. You can say tau goes from minus infinity, plus infinity, 1 minus tau, and then you break u of tau times this one. So it's always going to be t minus tau minus 2, and then u of tau times u of t minus tau, d tau. That's the first thing. The second integral is, so plus 1 minus tau, again, t minus tau minus 2, and then you have minus here, u of tau, u of t minus tau minus 4, d tau. The second integral, tau goes from minus infinity to plus infinity. The third integral is again minus, tau goes from minus infinity to plus infinity, 1 minus tau, t minus tau minus 2, then u of tau minus 1, u of t minus tau, d tau, and then the fourth integral is plus, tau goes from minus infinity to plus infinity, 1 minus tau, t minus tau minus 2, and the last thing is u of tau minus 1, u of t minus tau minus 4 d tau. So you have 4 integrals. Now it's the key step. Can we eliminate the boundaries, right? This one here gives you integral when tau goes from 0 to t, right?
Yes.
And this is 1 minus tau, u of, I don't need to write, u,
T minus tau
t minus tau minus 2, d tau. So that's the first integral. This is valid for t greater than 0. Every t greater than 0 would work for this one.
Sir, please don't give this kind of problem, otherwise we will solve just one problem in one and a half
It's okay,
hours.
it's not that complicated. Let's.
It will take a long time. It will take.
No, it will really take a long time because we're
But-
gonna use like u into
I
v.
know, but I
Yeah,
can,
that's.
listen, I can make these functions better. What if it's just this?
That would be better.
Yeah, so, I mean, let's
That's
just
a good-
figure out how you do this, right? Instead of worrying what's gonna be on the test. So let's look at the second one. The second integral, you still start from 0, right? And then you end up at t minus 4. But, and then you have 1 minus tau, t minus tau minus 2, right? T minus 4, right?
Yeah, right.
And d tau. But this is only working when t is greater than 4. This integral before t is equal to 4 is 0, right? Look, the boundary is 0 to t minus 4. So for this to work, this one is applicable only for t greater than 4, right? Let's call this integral I1. Let's call this I2. Now, we go through this one, and this is integral tau goes from 1 to t, right? And then you have 1 minus t minus tau minus 2 d tau. But this integral, you know, t has to be greater than 1, right? You cannot integrate before. And then the last one is integral when tau goes from minus infinity to plus infinity. You have, no, sorry, not infinity, plus infinity. It goes from 1 to t minus 4. And then here, 1 minus tau, t minus tau minus 2, d tau. And for this to work, t has to be greater than 1. Actually, it has to be greater than 4, sorry.
5, say.
Is it 5? No.
1 to, tau is from 1 to t minus 4, so t minus 4 should be greater or equal to 1, so t greater or equal to 5.
It's not 5, Excellent, you're right. 5. So now, if you look at, this is I3, I4, and then you take your t-axis, and then you start 0, 1, 4, 5, right? So this one, I1 operates for all of these t's, right? I2 only comes in play here. I3 only comes in play here. And I4 comes in play here. So you have how many cases? You have the case 1, t between 0 and 1, which is, in that case, you just have I1, in that case, right? Then you have case 2, t is between 1 and 4, in which case you have I1 plus I3. Then you have a 3 case, which is t is between 4 and 5, in which case you have I1 plus I2 plus I3. And in case 4, t greater than 5, in which case this is I1 plus I2 plus I3 plus I4, but we know it's identically equal to 0. We don't have to worry about the fourth range, because the duration of this signal is equal to 5. Go ahead.
After you got 1, 2, 3, 4 like that step, are you going to substitute that?
You have to shift it back to the left again, right?
At the very end. At the very end, I would have to shift it back. But I'm not worrying about it. These I can evaluate, right? This is, there's nothing here magical, right? This is, you cross multiply.
You just need to like
Substitute, right?
substitute it, yeah.
Substitute, right? What you remember the tricky part here is from where to where I integrate. Even when you flip and shift, you look at when the things are starting to change. But here, I'm kind of following the process where I don't have to flip and shift. I do everything analytically, right? And you see how we did it. We took the original one, broke that into integrals. You start by minus infinity to plus infinity. But then you look at what are these u's here, and then you make sure you set the boundaries of the integral correct. The lower boundary is going to be always given by u of tau of some sort. So it will be either 0 or 1 or something. Upper boundary is going to function t, but it will give you always the range of t's for which it makes sense. Like, look at this here. It goes from 0 to t minus 4. T has to be greater than 4 for this integral to have any value, right? Otherwise, you're integrating where the lower boundary is smaller than the upper boundary, right? So this tells me this integral only exists when t greater than 4. And then you kind of go through this step, and then you plot your t-axis, put the boundaries of interest, and then see which one of these integrals plays the role. And in this case, I have 3 cases. I have a case 1, which is just for t between 0 and 1, and I can evaluate only this integral for that case. I have case 2, which is for t between 1 and 4, and in that case, it's going to be this essentially minus this, right? Because there are minus signs here. So whatever I get here minus whatever I get here, right? And then in this part, between 4 and 5 is going to be I1 minus I2 minus this I3, right? And then I have the 4th interval after 5. But I can do that one just for exercise because I know the result. What is the result going to be? 0, right? Because I know that it terminates at 5. So now I have to do these 3. I can get it.
The 2 minus over there, you need to flip that first, or you just shift that?
No flipping. I'm not doing flip and shift here. I'm doing everything analytically. There's nothing. Did I mention flip and shift? No.
No, if we want to draw the graph.
If you want to draw the graph, well, you're going to have analytical. You're going to have for each one of these, you're going to have a function of t. Let me just do the first integral. So let's look at the case 1.
So is it possible for you to solve case 2? Case 1 seems to be easy.
The integration is going to be the same, it's the limits that change.
That's it.
Yeah.
Yes. So all of them are easy. Let's just, but the trick is to solve 2, I need to solve 1, right? So
Yeah.
you're just asking me to do one more step, right? But let's do 1. So I have to solve this integral. So it is, so I1 is, what's the best way to do this? I can say that this is integral when tau goes from 0 to t. And I'm going to write this as tau minus 1, put minus here, and then call this tau minus 1 minus t plus 3, and then put another one here, and then call this d tau minus 1. Let's see if this works. I flipped the sign in both of them. So you have tau minus 1 in the first parenthesis. In the second, you have tau plus 2 minus t. But this plus 2 I have written as tau minus 1 plus 3. Right? And then I added here this tau minus 1. So I can say that this is integral when, and I can introduce now substitution, x is equal to tau minus 1. So x goes from minus 1 to t minus 1. x minus t plus 3 dx. Right? So this is an integral from minus 1 to t minus 1, x squared dx minus t plus 3 integral from x goes from minus 1 to t minus 1 of x dx. Right? So this ends up being x to the power of 3 over 3, evaluated from minus 1 to t minus 1, minus t plus 3, x squared over 2, x squared over 2, evaluated from minus 1 to t minus 1. And then if you substitute, this becomes t minus 1 to the power of 3 divided by 3 minus 1/3 minus t plus 3 t minus 1 squared over 2. And then here minus t plus 3 over 2, if I didn't make any mistake. So that's your function in that interval, right? Between 0, 0 and 1. Okay? This can be a little bit tidied up, but not much, right, unfortunately. So you can see, to draw this, you have values of t. You have the function in that interval. So you just plug in t, you get a value. Okay?
So we put the upper and lower limits of t, 0 and 1.
So again,
How do we put values of t in that now?
I already put that. This is just a function of t.
Okay, sorry.
Yeah? So it's already there. Okay. So that's a long problem. It's not particularly hard. It's just there's a lot to do. Any other?
That looks like the one we did.
Hmm?
That's what we got.
That's the hardest one.
Yeah.
That's about what we got.
Any other problem?
The one on the population or something?
That's chapter 3.
3.4
Yeah,
dash
chapter
2?
3, right? Yeah, 3.4. Huh? 3.4 dash 2.
There's 2. Let me, oh, okay.
Oh, it's not that.
Let's see.
I don't understand how they get there.
It's not that hard. Yeah, it's not that hard.
So
I thought that.
3.4-2. It says let P of n be the population of a certain country at the beginning of the n period. So P of n, population. And P to n. The birth and death rates of the population during any year are 3.3 and 1.3% respectively. So the birth of in the nth year is going to be 3%, or I should just write 0.03 of P of n. And the death rate, birth rate, and death rate is 1.3%, so 0.013 times P of n. Okay? And if I of n is total number of immigrants entering the country during the nth year, write the difference equation relating P of n plus 1, P of n, and I of n. Assume that the immigrants enter the country throughout the year at a uniform rate. Right. So here's what we're saying. It's just a little bit, you gotta think. You're saying, what is the population at the n plus first period? It's gonna be whatever it was at the nth period plus 0.03 P of n. So whatever is that there were people before plus whoever was born minus whoever passed away, and then plus whoever immigrated into the country. Right? It's just as simple as that. So if you now think of this, you can take this and rearrange it differently, and you end up P of n plus 1 minus, so this is 1 plus 1.03 minus 0.013, so it's going to be 1.017, right?
Yes.
P of n is equal to I of n. So that's the difference equation that describes the population growth, in this particular country. And what kind of difference equation this is? This is a first order difference equation. So what does the population look like here? I can say the population at any n is going to be C1 times gamma to the power of n. That's your plus impulse response time convolved with I of n. Right? This one I can calculate by solving characteristic equation. This one I calculate the impulse response, and then I can calculate whatever is that what he ultimately
Oh,
wants?
what's I of n?
I of n is number of immigrants, right?
What is it? It's gotta be in the form of P of n.
So, but that's it, right? You just write that's what they wanted. Just write the difference equation. I thought they wanted to solve it somehow, but that's it. Any other? No? All right. Well, I didn't manage to post. I'll try to post them tomorrow, so there will be a whole bunch of problems posted on the web. And just prepare yourself. It's not going to be hard. I mean, I'm not going to give you this. But it may be something like this. So it's not going to be this complicated. It's not complicated. I'm trying to make it not as complicated. I try, sometimes I fail.
Professor.